Hello, my name is Mason, and I will be showing you how my group solved for the ratio of the flow rates exiting our Venturi mixer design. So to start solving for this, we are going to start with our Bernoulli equation. Okay, so I'm going to do the Bernoulli equation between points 1 and points 3. So we fill that out. Okay. And one thing to note, this Bernoulli equation is going to take into account the head loss, and we will use the Darcy-Weisbach equation to solve for that, but we will get there in just a moment. So the first thing with Bernoulli equations that we're going to do is that we are going to cross out the values that are either equal on both sides or that are 0 in value. So point 3, this is the exit of our Venturi, so that is going to be at atmospheric pressure. Atmospheric pressure will be denoted as 0. So pressure 3 will go to 0, so we can cancel that term out. The other terms we can cancel out, the difference in height between points 1 and point 3 is a negligible value, so we can cancel that out on both sides. Okay, if we do a little bit of rearranging this equation and just go ahead and rewrite it out, we're going to get P1 over gamma plus V1 squared over 2G equals V3 squared over 2G plus our head loss. Okay, and now at this point, we need to figure out what our head loss is actually going to be. So like I said, we're going to be using the Darcy-Weisbach equation to actually solve for it. Okay? But the thing to note is that the Darcy-Weisbach equation requires a velocity and a diameter to be solved for. And for sections 2 and sections 4 here, our diameter and our velocity is not constant. Therefore, it makes the Darcy-Weisbach equation a little more difficult to use. What we can do to use this equation, though, is we can just take an average diameter between those points. So if we look at the average diameter for section 4, the average diameter for section 2, we can use those diameters in the Darcy-Weisbach equation to solve for our head loss between those points. And then using our average diameter, we can find an average velocity as well, knowing the flow rate through there. Okay, so for this case, we have 4 different sections, section 1, 2, 3, and 4. So we're going to have 4 different Darcy-Weisbach equations. Okay, and our total head loss is going to equal the sum of each of those Darcy-Weisbach equations. Okay, so we have the head loss for 1, 2, 3, and 4, as denoted right here with our green marks. Okay, so the head loss through 1, like I said, we'll be using the Darcy-Weisbach equation, which is going to be our friction factor times the length over the diameter times the velocity squared over 2g. Okay, and this is going to be for 1, so I'm going to put a 1 in front of these to denote that it is for this first section. Okay, so how we go about finding these values is for our friction factor, we have to know a Reynolds number. And then we use the Kohlberg formula with the Reynolds number and the roughness of the pipe, and we can find our friction factor. Now, we do use Microsoft Excel to do this because it is not an equation. The Kohlberg formula is not an equation that can be solved implicitly. So we have to use some sort of computer iterative solution, such as GoalSeek within Excel. So that's how we get our friction factors. The length is something that we can find from the dimensions that we've made the Venturi ourselves. The velocity is known because we have a known flow rate and a known diameter. Therefore, we have a known velocity. Diameter, like I said, it is known because we dimensioned the material ourselves, and then g is just the gravitational constant. Okay, and then so that's for section 1, and then for section 2, it's going to look a little bit different. So we're going to have the friction factor for 2, and one thing to note is that the friction factor for each of these sections will be different because the Reynolds number for each of these sections will be different. If you have a different Reynolds number, you will have a different friction factor, and that is what is going on here. Okay, so section 2, different friction factor. It's also going to have a different length, but that is something that is known because we dimensioned the material ourselves. And then it's going to be the average velocity through section 2 squared over the average diameter of section 2 times 2g. Okay, and then HF3 and HF4 look very similar to 1 and 2 respectively. HF3, we don't have a expansion contraction. It is a constant diameter, so we can just solve it using how we normally solve a Darcy-Weisbach equation. But for section 4 is that expansion, so we're going to have to use the average diameter and the average velocity again for section 4. So once these values have been determined, we then know our total head loss, and the total head loss is put into this equation to solve it out completely. So this is the first equation that we use to solve our system of equations that we're going to get after we generate our other equations. So in total, there are 4 equations, 4 unknowns, therefore we need 4 equations. And this is the first equation with our unknowns. I'm sorry, I didn't write out the unknowns, but our unknowns are going to be the pressure at 1 and the velocity at 3. We know the velocity at 1 because we know the diameter at 1, and we know the flow rate at 1. It's the flow rate of our pump. Okay. So if we just solve this, do a little bit of rearranging with this equation right here and write it out, we're going to get that P1 equals gamma times V3 squared minus V1 squared over 2G plus R plus. Okay. And that is the first equation that we will be using to solve for our system of equations. Okay. I will now be showing you how we solved for our second equation in our system of equations that we use to solve for our flow rates exiting our Venturi. Okay. So, like the first equation, we're going to be using the Bernoulli equation, and that's going to be where we're starting. We're going to be using between points 2 and points 5. So point 2 is in between the skinny part of our Venturi, and that is actually where the low pressure area is going to be, and what is causing this fluid to be pulled up through this tube. So we needed low enough pressure at point 2 that will actually cause this fluid to go up the tube and actually mix the fluid as it's supposed to. Okay, so we're in our Bernoulli equation, and we still have a head loss as well that's going to be taken into account. But first, let's look at values that we can cancel out on either side. So first thing to notice is that at 0.5, this is a free surface at atmospheric pressure. So since at atmospheric pressure, that value at pressure 5 is going to go to 0. Okay. The velocity at 5, we're also going to say is a negligible value. There is a velocity going on at 0.5 because that water is going to be mixing, therefore we're losing water in this tank, and the water level will be lowering. So it will have a velocity. However, we are trying to design it such that it is a greater area, cross-sectional area. Therefore, the height won't be going down as quickly, and that velocity will be as low as possible. So we're going to assume that velocity to be 0. And then the other thing to note is the difference in height between 2 and 5. So Z2 minus Z5, that's going to be equal to our value H that we have right there. Okay, so if we do a little bit of rearranging with the equation, I'm going to write it out. And then Z2 minus Z5 is H, so we're going to add H to this side, and that's going to equal our head loss. Okay, so at this point, the values that we do not know are going to be P2 and V2. So those are our two unknown variables in this equation. I'm going to fill that in over here. P2 is unknown variable, and V2. Okay, so at this point, we have seen all 4 of our unknown variables. At this point, we are generating those 4 equations to solve for these 4 variables. Okay, so back to this equation. At this point, we need to start looking at our head loss. Okay, so we're going to be using the Darcy-Weisbach equation to solve for the head loss. So Darcy-Weisbach equation is F L over D V squared over 2G. Okay, so how we solve for the values here. Our friction factor for our head loss is going to be found from the Reynolds number. The Reynolds number and the roughness is used with the Colbert formula, and we use goal-seek within Excel to solve for the friction factor. That is no different than we did in part 1. However, we're going to have a different Reynolds number that is actually for this tube right here. Okay, the length of this tube, so the length between 2 and 5, the distance between points 2 and points 5, is just our distance h. Okay, so in this case, we're going to say L is equal to h. The velocity in this case is going to be what V2 is. So whatever V2 is going to be our velocity. Okay, V2 is this velocity that's actually of the fluid actually moving up. Okay, diameter is a known value from the dimensions of our Venturi, and then G, our gravitational constant. Okay, so for this case, we kind of fill in some variables. Our total head loss between points 2 and 5 would be the friction factor between points 2 and 5, H times V2 squared all over 2 dg. Okay, take that head loss, and we plug that value into here, and that allows us to finish solving this equation. So if we write out what this equation is actually going to look like, it is going to be P2 equals, sorry, not P2, V2 equals HF minus H minus P2 over gamma. And then all of that will be multiplied by 2G, and then all of that will be underneath a radical. Okay, so that is the second equation that we use to solve our system of equations. All right, I will now be showing you how we got our third equation to solve for our system of equations to find the ratio of the flow rates exiting the Venturi. Okay, so like the first two, we're going to start with our Bernoulli equation, and we apply the Bernoulli equation between points 1 and points 2. Okay, so when we apply the equation, likewise for the first two, we are taking into account head loss this time. So when we apply the Bernoulli equation between 1 and 2, we need to cancel out values on both sides that are equal on both sides. So in this case, the only thing that we can definitely cancel out is going to be Z1 and Z2. The height difference between points 1 and points 2 is negligible in this case. Therefore, we can cancel out on each side. Okay. However, all these other values are not equal on either side and not 0 in value. Therefore, we're going to have to leave those values. Okay. Another thing to note about this equation is I know we are applying the Bernoulli equation between points 1 and 2. However, this velocity isn't what we've already denoted as V2. We denoted V2 as the velocity of the fluid coming up through this tube. That is V2. Therefore, the velocity at point 2 of this fluid flowing through is going to have to be a different velocity. Okay? And we call that V4. Because V4 has yet to be used. Okay? If we were to rewrite the Bernoulli equation, we could get to P1 minus P2 over gamma equals V4 squared minus V1 squared all over 2G plus our head loss. Okay? And then at this point, we need to figure out what the value for our head loss is going to be. Okay. So head loss, just like the first two equations, we're going to be using the Darcy-Weisbach equation. However, we're going to have different sections again because we have sections with different diameters. So we have section 1, of course, right here, section 2, and then section 3. So we have 3 different sections in this case. Section 2 is the only section that does not have a constant diameter and a constant velocity. So we take the average diameter and the average velocity, like we did for the first equation. Okay, so HF, our total head loss, is going to be the sum of our head losses, HF1 plus HF2 plus HF3. Okay, and then to actually solve for each individual head loss, we got to look at the frictional factor between each section, which is different for each section because each section has a different Reynolds number. Okay, so we multiply the length of that section over the diameter of that section, which might be the average diameter if we were for section 2, times velocity in that section over 2 times the gravitational constant. Okay. And then for section 2, we're going to, of course, have our friction factor times the length for 2 over the average diameter for section 2 times the average diameter, the average velocity for section 2 squared all over 2G. Okay. And then the head loss for 3 is going to look very similar to the way that we saw for the head loss for 1 in this case. It's just going to be the length for, through section 3 we're going to be using, and then it's a constant diameter, therefore a constant velocity. Okay. So if we look at this equation right here and do a little bit of rearranging, we can get that equation to read P2 equals P1 plus gamma times V1 squared minus V4 squared all over 2G minus our head loss. Okay, so these are the 3 equations that we've come with so far. We have one more equation to generate, and we'll get to that in just a moment. Okay, now I will show you how we got our 4th equation to solve for the ratio of our flow rates exiting our Venturi. Okay, so the 4th equation is the only equation we use that does not start at the Bernoulli equation. This is actually going to start at the mass flow rate equation. So conservation of mass flow rate in has to equal mass flow rate out. Because our density is constant, we could just write that as our flow rate in has to equal our flow rate out. Okay, so if we sum up all of our flow rates in, we're going to get Q1 coming in and Q2 is coming in. So Qin is going to be Q1 plus Q2. And then our flow rate going out, the only flow rate we have going out is going to be Q3. So Q1 plus Q2 equals Q3. Okay, and then we can reuse the continuity equation and rewrite this in terms of its areas and velocities. Okay, all of our areas are known because all of our diameters are known from the dimensions of the Venturi. And then we also know V1 because we know the flow rate of our pump and the diameter of our entrance. Therefore, we know the velocity. Okay. Keeping in mind that the area for this is going to be pi over 4. times the diameter squared. We can rewrite all of this in terms of its diameter. Okay, so A1 is going to be, well, we'll just convert this. All of the pi over 4 will be pi over 4 in every term, so we'll just divide it out of every term. Okay, so d1 squared v1 plus d2 squared v2 equals d3 squared v3. Okay, and then we can rearrange this equation to solve for v3. I'm going to write that over here. So v3 equals d1 squared v1 plus d2 squared v2 all over d3 squared. Okay, and now that we actually have all 4 of our equations, we can solve this system of equations. Now this system of equations is something that cannot be done implicitly. It has a circular reference within it as v2. There is a variable v2 inside of this, and it's just not something that you can solve with a pen and paper. You need a computer or calculator in order to solve this system of equations. So we use the iterative solution tool in Excel, and we actually solve this system of equations, and we can get numbers for all 4 of these values. So we know P1, V2, P2, and V3 at this point using these 4 equations. Okay. So once we know all 4 of these values, we just need to know the ratio of our flow rates exiting right here. So the ratio of our flow rates exiting our Venturi is just going to be Q2 over Q1. And at this point, we know V2 and V1, so we could write that as D2 squared V2 all over D1 squared V1. Okay? And that is actually how we're going to solve for the ratio of our fluids exiting the Venturi. Okay, now I will demonstrate for you how we calculated the uncertainty of our measurements. Okay, so how we calculate an uncertainty is a little more intuitive than it is actual practical. The reason I say that is because all these values aren't actually calculated values. Instead, they're values that we kind of just place on the experiment based on how our tools work and how everything functions and all of that. So the 5 different things that we have on our uncertainty budget are repeatability, stability, bias, drift, and resolution. And then we're going to assign a percentage value of uncertainty that each of them have based on the materials that we're using in our experiment. And then we're going to use this equation in order to solve for our total uncertainty of our experiment. Okay? So this serves more as a sample calculation of how we're going to solve for uncertainty, because once we have a real good data, we can put better numbers on these uncertainties. Okay, so first, repeatability. How repeatable is our experiment? Our experiment is rather repeatable. The only issue that we have with the repeatability is how strong it is. We do have to use Flex Seal on parts of it due to some errors in the 3D printing process. However, it is quite repeatable with now that it has a Flex Seal on there and everything. It's just a matter of that holding its strength. So we put a value of 3% on there, or as a decimal, it'd be 0.03, but I'll write that as 3%. Okay, the stability of our experiment. So is our error changing over time? It isn't changing over time too much. There would be a little bit of wear on the inside that would smooth out the inside surface of the pipe, causing maybe a little bit less head loss in the Venturi over time. However, it's not that significant, and it's not something that needs to be taken into account too much. So we just put a value of 3% on there. Okay, the bias of the experiment is a little bit different. So if it tends towards one direction or the other, unfortunately for our system, it's going to tend towards the starting point a little bit more. The reason for that is because it's going to, whenever we turn on the pump and create the low section area, it's going to take a bit of time for it to actually get to that flow rate that we predict it's going to be. It's going to take time to get to a working state. Because of that, we included our bias to go up a little bit more. We put that at 4%. Okay, and then the drift, how likely is our errors going to be sliding, changing, that kind of thing. Really not that much. It's very similar to stability. It's not going to be changing too much over time. The only thing that's going to be changing is really maybe our head loss a little bit, but it's not a significant factor to be taken into account. So we just put a value of 3% on it. Okay. And then the resolution is the biggest source of error in our experiment. The reason for that is because how we're measuring the flow rates is we are measuring the amount of fluid that is flowing over a certain time. So what we did is we made marks on the tanks where the fluid was leaving and entering, and we just measure the time it took for it to go between those marks, which using the naked eye, measuring out 10 liters or whatever amount of fluid it was that we measured at the time, it's not 100% accurate. There is definitely a source of human error in there. So because of that, we put our resolution up to 7%. Okay? And then if we convert all of these to decimals, so 0.03, 0.04, 0.07, and square it, take the square root of those and get to a number. If you plug everything in, you should get to a number somewhere to 9.6%. And that is going to be our total uncertainty for our experiment, how uncertain the ratio of the flow rates leaving the Venturi is. Okay. Thank you.
Hello, I will be discussing how we use Microsoft Excel to solve the circular reference of equations. Okay, so first thing, since you're solving a circular reference of equations, you need to make sure that iterative calculations is enabled. You do that by going to Options, Formulas, Enable Iterative Calculations. And this number right here represents how many guesses your computer would make before it reaches its answer. So in this case, I have it set to the maximum value that Excel will allow. Okay, this spreadsheet you're seeing here does not take into account any frictional losses. And this spreadsheet here does take into account frictional losses. And anything you see that highlighted in blue is an input value, so something that has to be inputted. And then anything that is not highlighted is a calculated value. Anything highlighted in green is an answer, something we're looking for, such as our mixing ratio or our 4 unknown variables. And then hashtag num, this happens from occasion. This indicates an impossible solution. So this hashtag num indicates that we will not get any mixing. This could happen if our height increases too much or if our flow rate decreases too much. Okay. So for example, if I increase our height from 15 centimeters to 50 centimeters, we see that we have an impossible solution. So this height is too great for us to actually cause mixing. One thing I've noticed about Excel is that you can't just revert back to your solution because of all of these errors. So you have to put in a value for one of the variables. So in this case, I'm going to input 0 for V2, and then you can paste the equation back in and it will solve the series of equations. Solving this series of equations, one thing to note is that you need to goal seek this column to equal 1. This is from our Colebrook formula, and this will solve for the friction factor when you do this. This doesn't change your answer greatly, however, it does change your answer. This green right here is our mixing ratio that the spreadsheet solves for. And in this case, we're getting about 2.5 for our ratio. And in our experimental results, we were getting closer to the mid-50s, somewhere around 55, 56. Now, because of the experimental versus theoretical results, one might say that this spreadsheet is not valid and that the equations in here do not hold value. However, there are many errors in our experimental results that cannot be taken into account for in our Excel spreadsheet. One of the main ones is the pressure. So in order to create the suction in the throat of the tube, we have to create that low pressure area. So no outside air can be entering the system, otherwise it's going to increase the pressure in that throat and it is not going to cause suction. This is one of the major sources of air in our Venturi design because whenever we started the Venturi, it originally started spewing water, and we had to use a rubber sealant in order to cover the Venturi. Now, any air holes that are in this Venturi will cause extreme fluctuations in our results, and this is what is causing the fluctuations in our results. So all of this spreadsheet is reading a ratio of about 2.5. This would be in a 100% perfect idealization environment. The only thing that is not idealized is the friction loss. If we were to design a Venturi with higher quality build materials and a little bit bigger, and we given more time, we could get this the experimental mixing ratio a lot closer to our theoretical mixing ratio. However, this theoretical mixing ratio is the most perfect mixing ratio that we would be able to achieve experimentally.
So the video we're going to show now is our first test of our Venturi. It actually does not work in this test, and we thought it, was something wrong with the design and that it wasn't possible for this specific design to work. But then we noticed a lot of the water appears to be leaking out of the sides, as you can see in the video here. It was almost like the Venturi was made of a porous material, and we came to the conclusion that it was just the way that it was 3D printed. So we determined that there wasn't a negative pressure being formed inside the Venturi to actually suck the liquid up like it was supposed to. So you'll see how we kind of combated that issue and fixed our problem here in just a second when we move forward to our second test that actually did work. So now we've got our experimental setup here that we'll show you. Essentially, as you can see here in this video, we have our Venturi mounted on some 2x4s, and that's our edited Venturi that you see there after we've made some modifications to it, as we'll discuss here in just a second. But basically it's hooked up over our bucket of suction or mixing fluid that's being sucked up through the Venturi and mixed. And how it works basically is we have our hose connected to a water spigot on the exterior of a home, and that flows to a flow meter that's oriented vertically, as you can see, and then it flows through another hose that goes up to our Venturi. So now we'll show a video just kind of proving and showing that the Venturi actually does work. So in this first video you'll see, and actually you'll be able to hear in the audio, that the end of the tube on the suction end of the Venturi is sucking in air, and then when we pour in water into our bucket you'll actually see the water suck up into the tube and be able to hear it as well. So we'll play that now. So this next clip is something we're calling the food coloring test. So as you'll see in the video, we take some food coloring and we squirt it in our bucket just there around the suction end of the nozzle. And as you can see there, you can actually see the food coloring get sucked up into our tubing there. So this kind of just validates that it does work and everything, and we'll do it again here. And you'll see the food coloring get sucked up into our tube. That was a little bit better one you can see there. So for our last clip here, we have a video of us measuring the actual flow rate at the suction end of our Venturi. So you can see on this bucket here, we have half a gallon and 1 gallon marked. So what we'll do is we'll turn on our Venturi and we'll let the system kind of flush itself of any air bubbles that may be lingering in it. And then we will submerge the suction tube in the water, start a timer at that point, and measure the time that it takes for half of a gallon to drain from our bucket. So as you can see, we've sped up the video here as well, because the process of draining a half of a gallon from our bucket actually took approximately 4 minutes. We ended up having a flow rate of 5.8 gallons per minute at the inlet that held constant throughout the process. And after doing some calculations and measuring our time, we ended up getting 0.12 gallons per minute at the suction end of our Venturi. So as you'll see here, we ended up taking 4 minutes and 10 seconds roughly to drain half a gallon, so you can estimate 8 minutes and 20 seconds to drain a full gallon. So doing some math and calculating our ratio, we ended up getting a 1:48 ratio, which what that means is for every 1 part of concentrate you have at the bottom there in the bucket, you would have 48 parts of incoming liquid.